my first batch student, I taught him microprocessor.
Very good. Thank you.
When I was seeing his notes, it is not the exaggeration. When I saw his notes is much, much better than my notes. It is a fact. So that's the way how he writes, how he was punctual, first bench, and even today is like that only. And after completion of BTech, is GATE first ranker.
Seventh.
Then he joined IISc Bangalore, and it is MTech, he did PhD. Now other parts, that's what she told. So tell about him. Other parts she will tell. This is enough for me.
That's
so
enough, sir.
actually there is one what I can say, because we are all teachers, we all expect that we should get Best Teacher Award. But till 2024, I didn't receive for various reasons. But it is the first person on every September 5th, he greets me. So his greetings are again better than or higher than receiving award from government of Telangana. So this is what that 2004, 20 years, who remembers? So that's what. So even today also he says, dear sir, like that, right?
Thank you very much, sir. Really touched. We'll get started. So I'm from Micron here, and we are into DRAM design. So I'll give you an overview of DRAM today, where it stands, what are the different application space that it caters to, and the future trends in this. So this is the outline that we have for today. I'll introduce you to DRAM. Probably you might have seen some sort of memory in your course curriculum. DRAM is one such memory. I'll talk about the various products that it caters to, and then we'll delve into a bit more details on DRAM, basic operation, and then two specific generations of DRAM, LPDDR4 and LPDDR5. I'll introduce you to those, and then we'll talk about technology scaling and also the state of the art and future trends. So let's get into the introduction portion. So most of you might have heard about DRAM. You might have used DRAM unknowingly or knowingly. So even in your phones, right, you have this configuration 4 GB RAM, 6 GB RAM, 8 GB RAM, 12 GB these days. So all that is DRAM. And similarly, in the laptops, right, you have the various configurations these days, 8 GB RAM, 16 GB RAM. So all that is DRAM. And if you look at this numbers, right, this is a bit dated, but still it will drive home the point. So in 2017, Micron, by the way, is one of the companies which manufactures DRAM. There are 3 different companies on the world. So Micron is like 20 to 30% of the share. So if you look at the number, right, it's mind boggling. It's like 10 raised to 18 DRAM bits in one particular year. And if you were to see, right, overall industry, it's like 400 quintillion is 10 power 18. So that's the amount of DRAM that gets generated year on year. And it's like every person in the world, right, is using about 6 GB of RAM. So that's the kind of pervasiveness that DRAM has. Now coming to different types of memory, right, so you might have seen this pyramid structure prior. I'll just reintroduce this to you. So at the top of the pyramid is your CPU. So that's your core in very close proximity to your CPU. Then you have L2 and L3, which is slightly next far away. And then you have the system RAM, and then the permanent storage. The permanent storage is like your SSDs and HDDs. And then for these days, we also have network storage. So the Googles, Amazons, and all support network storage these days. So that is like far off from your actual computing paradigm. So where does DRAM play into this? So this is where DRAM sits. That's the system RAM. So it's in between your cache and the permanent storage. So if you just go down this thing, right, you are actually going to get cheaper and cheaper, but the processing time or the access time would be on the higher side. But if you just go up this pyramid, your dimensions are going to get shrunk, and the processing speed or the access times are going to be much better, much faster, and it's going to be costlier as well. And it's dynamic because it's actually stored on a capacitor, and you will have to refresh it periodically because charge gets lost over time, and you will have to have a periodic refresh somehow built into the system. So that's why it's dynamic in nature, as opposed to the static RAM, wherein you have a cross-coupled inverter structure, which will hold data indefinitely as long as you have it powered up. random access you can access from any portion of the memory array from one particular bank or one particular row, right? If you have accessed something, you can access it from a completely different space. So that's why it's not sequential or ordered in that way. And then of course it's a memory, a large scale memory that we are talking about here. So this is just an analogy wherein we are talking about a library model. So let's say we have a library, we go fetch a particular book or few books, get it to a desk, and then now we are ready to start our reading. So let's say we have started reading from one particular book. So the page that you have currently open, right, it's like that data is readily available for you to digest. So that is like your cache memory. So now if you just flip, that's like your register memory, right, if you were to call it. So if you just flip the pages, that's your cache memory. So you still have data available within a fraction of a second. And then if you feel that, okay, you are reading a particular book, analog integrated circuits from say Razavi, and you now want to go to Professor Mayer's book, right, that's the next book on your table. So that's still available. So that's like your DRAM. So the access time is slightly higher, but still it's within reach. Now if you are completely do different things, so you have been reading analog and now you want to switch over to digital and you are going back to fetch Rabe or something, right, to the shelf. So that's like your storage, access from your storage. So it takes much more time than your either cache or RAM. So I'll skip this in the interest of time and just move to, yeah, this slide. So DIMMs, so DRAM as a product, right, are used in multiple domains. So one such thing is DIMM. This is what you would see in your laptop. So if you break open your laptop or desktop for that matter, right, you will have DRAM DIMM modules. So DIMM stands for dual inline memory module. So it actually houses multiple DRAM chips in a small PCB like structure. So what is there over there, right, that example that you are seeing over here. So yeah, so this one. So this is a DIMM module. So each one is a DRAM chip, and typically you will have about 8 or 16 of such chips in this, and all this yellow colored things are your connectors that will connect to your controller or the CPU. So it typically you would need a 64-bit of data to interface with your CPU, and DRAM typically supports either 4, 8 or 16 bits of data from each chip. Typical configuration, right, within those is 8. So if you take 8 data coming out from DRAM and you need to now have a 64-bit data to be interfaced with your CPU, you would need 8 such DRAM chips. So 8 DRAM chips will be housed in that particular small PCB board, which is called your DIMM, dual inline memory module. So this is what you would have as your DRAM's memory slots in your laptop. Now coming to the products overview, right, so as I said, DRAM caters to multiple different domains, different application spaces. So few of them are listed here. So one is called compute DRAM. So this is what you would you'd be using it for your laptops and servers and data centers. And graphics is predominantly for your GPU applications and to some extent data center applications as well. The next thing which is very recently has emerged out is called HBM DRAM. It's called high bandwidth memory. So of late you might have heard this buzzword, right, generative AI, chat GPT and so on and so forth. So what does this do as compared to your conventional search engines, right? So now you are able to generate data as opposed to just doing a brute force search. So now if you are able, if you are giving in search in chat GPT or whatever, right, it's able to gather a lot of data and then it's able to summarize it and probably create more content from its own. So for all that, right, you would need a huge amount of memory and HBM is one such memory wherein you can have a large amount of IO which can drive home such applications. So HBM is one. And mobile DRAM, of course, this is something that we have been using day in and day out. We have been using smartphones, and all smartphones have memories. It has both DRAM as well as SSDs, and LPDDR is the DRAM portion of that. So just to summarize, right, whatever we have seen so far, so the actual use case of each of these memories. So the snippets that you see here are from the computing domain for it's the laptop or the desktop, right. So that's where your DIMM modules would be sitting. And then to the right, the center one is your LPD RAM. So that's your mobile phone. So if you just break open your motherboard, right, of your LPD RAM, I mean your mobile phone, you would see something of this nature, and this is where your DRAM chips reside. And HBM is an emerging memory, as I said. So this, along with graphics, is being used for data centers and generative AI applications. Now let's get into a bit more detail on the terminology that is being used in the DRAM world, right? So DDR. So this is a common terminology that you will see pertaining to DRAM. So DDR stands for double data rate. So in a conventional digital design, the way it operates is you have a master clock, and at every positive edge or negative edge, based on how the system is designed, you have data coming out. So it's like you have an edge and you have a data coming out, and you have the next edge and the next data comes out. So that's like a single data rate at every edge. But here we make use of both the edges. So that way you can actually double the bandwidth. So if you look at the diagram, the clock signal there, right, you have a pulse waveform there. You have a right positive edge and a negative edge. So this is your clock cycle. So typically, if you were to operate in a conventional design paradigm, right, you will have data coming out here, and the next data comes out here. So for every clock cycle, so if say they are using a 1 gigahertz clock, it's like a 1 nanosecond time period. For every 1 nanosecond, you will have some data come out. But now we will make use of both the edges. So you will have one data come out here, and then the next data packet comes out here. So even though your system clock is still 1 gigahertz, you are now getting data at the rate of 2 gigahertz. So that's the advantage that you have now. Bit more on compute DRAM. So as I said, we use this in the context of DIMM modules. And if you look at, if you have seen these DIMM modules in the laptop, right, this typically spans a few centimeters. So now this has to interface with your CPU. So the CPU will drive clock as well as data. And now you have DRAM chips lined up sequentially. So you need to have a mechanism wherein you can synchronize the clock that's been driven out of the CPU and reaching your DRAM, also with the clock, with the data that's been reaching it there, right. So that synchronization is done using an internal DLL. So every DRAM will have its DLL, so that whatever comes in, the clock as well as data are well synchronized. I'll introduce the concept of rank here. So as I said earlier, we have a 64-bit bus which will interface between your CPU and the memory, the DRAM. So now we have built this DIMM module. We have 8 DRAM chips, each giving us 8 bits of data, and say DRAM, each DRAM is 1 GB. So you have 8 GB in your system supporting whatever application that you want to. Now typically we go for upgrades, right, 8 GB to 16 GB. We go to a center and say, okay, I need my memory to be upgraded from 8 GB to 16 GB. So you add one more slot. So essentially what we are doing is we are creating an additional memory space, but still your bus is going to be 64-bit wide. So 8 GB is going to grow to 16 GB, but effectively whatever gets interfaced with your CPU is still going to be 64 GB, 64-bit. So how are we enabling that is through a rank system. So you will have a rank 0, which will interface with your memory if it's a single rank system. And if it's a multi-rank system, you will have a chip select to select between 2 of the ranks, so that when you are accessing one particular rank, you have 64-bit data coming from that 8 DRAM chips. And when you are accessing the next 8 DRAM chips, right, you will disable this chip select and enable the chip select of that particular rank. So that way you are now growing your memory size, but still retaining the same bus width. So that's the rank, which is very useful feature for increasing the capacity of your system. The other concept is called a prefetch. So earlier I talked about double data rate, wherein you have data coming out at every edge, right. So what if we extend this concept? So can we have more data come out for every edge so as to increase the bandwidth? So that's the thought process here. So we started off at single data rate. So that's the clock periods, and the DRAM internal clock is also the same. So let's say the clock was 133 megahertz. So translating to 7.5 nanoseconds of time period here. And your this is your system clock, and that's your IO clock, the CPU clock. So typically your IO clock, right, works faster. So if you are talking about Intel processor, right, that operates at a much higher speeds than your memory typically. So we have been seeing significant growth in the memory, processor regime, but the access time of memory is typically staying constant because of the kind of dimensions that we are working with. So even though there is no change here, we are somehow generation on generation improving on this access rates, speed. So this is how we do it. So we started off with SDR and then we go to DDR. So in DDR we take both the edges here and have data captured at both the edges. So when we are saying we are capturing data at both the edges, what are we doing internally? Because when you are doing a memory access, you give a row address and you give a column address. So some data comes out. Now we are saying, okay, we are going to take advantage of the next edge as well, which is not the actual positive edge, but the negative edge. So your column address or row address will get refreshed only on a cycle to cycle basis, but now we are taking advantage of an internal edge position. So the way we are doing it is internally, once an address is fetched, we will, rather than just fetching that particular data, we will also fetch the adjacent data. So which is like next column or next row based on how the architecture is defined. So that data also gets captured. Similarly, going to the next generation, rather than just capturing 2 data, we start capturing 4 data. So in effect, you have now quadrupled your frequency. And similarly, next generation was 8 data prefetch, and now it's like 16 data prefetch. So once you give a clock command with address and row address and column address pumped in, instead of fetching bits from that particular row and column address alone, we will fetch the neighboring ones, which is like additional 15 bits, so that you get a 16-bit information handy, and that will be sent out serially. So this is the prefetch thing. So at the start of the presentation, we said DRAM is dynamic random access memory. But now we are doing this prefetch, wherein you are saying, okay, one particular address is given. Now I will not just fetch that particular address, data from that particular address, but will also get data from 15 bits which are right next to it. So are we violating that randomness to some extent? To some extent, yes. But we are also exploiting the fact that there is typically data locality in whatever operations that we do. Like for example, if you are scrolling, right, scrolling your mobile phone, or you are taking a picture. So whenever you are doing such an operation and when you are fetching data, there is very high likelihood that not just that particular bit, but the bits right next to it are also needed. So we are taking advantage of that and prefetching the data. So conventionally, this is how it's been done now. So whenever you are doing access to the DRAM, it's not just one bit, but you get n number of bits based on what prefetch architecture that it's using. So this is how it is. So you have a row address and you have a column address. Like for example, this is what you intended to fetch. Say you've given this address 0110 and 1000. So you get 1 bit of information, but you don't stop with that. You actually change your column address all the way through and get all the 8 bits of information and have it readily available, so that can be sent out in one burst. Now coming to the device configurations, as I mentioned earlier, DRAM comes in various I/O configurations, either 4-bit or 8-bit or 16-bit. So this is the conventional, the LP DRAMs and the compute DRAMs. The HBMs have much higher I/O. I'll talk about that later. So this is the growth that we have seen in the DDR systems all through. So as time progressed, right? So for the past 20 years, 2003 all the way to 2020 and above. So what you are seeing is the effective system bandwidth. So what started off at say 8.5 gigabytes per second, now we are hitting greater than 50 gigabytes per second. So that's the kind of speeds that we have hit. We talked about compute a little bit, but on the mobile DRAM. So as LP stands for low power DRAM, low power DDR DRAM here. So low power because it's going to sit in your memory device or IO device, tablets and so on and so forth, right, which are typically battery operated, and you don't want your battery to drain out faster. So you want your mobile phones to hold the charge at least for a day or so, and since DRAM is one such device which actually sinks in a lot of power, you need to ensure that it's not as power hungry as the other components within your PCB has. So LP DRAM is specifically a low power design technique that we employ in DRAM to ensure that we can sustain that battery life. Graphics is again, graphics is typically used for GPU applications and data center application, and this also caters to much higher bandwidth than your conventional LPDDR and compute DDR. A slide on the speeds here, right? So you talk about generative AI and talk about the amount of data that we are using. So this gives you a context of the kind of data speeds that we are looking for and the kind of volume of data that we are trying to access. So this is how a GPU with a memory system is built for a typical AI application. So this could be your AMD chip or NVIDIA chip sitting here, and then this will interface with multiple DRAM chips here. So each of this is a DRAM chip. So in this particular example, we have one GDDR, each one is GDDR, and this is a GPU. We have 12 such dice here. And if you look at the pin level bandwidth improvement, right? So we started off with 8 gigabit per second. So this small b is a bit, 8 gigabit per second, going all the way to 21 gigabit per second with the GDDR6X. So each number here denotes a technology. So 5, 5X, 6, 6X are the different technologies enhancements that we have done over time. And then this is at the pin level, and then comes the configuration. So earlier I showed that we have by 4, by 8, by 16. So those are for compute and LP. For graphics, we have much higher I/O. It's like 32. So then once you multiply with 32, you get a device level bandwidth. So when I say device level bandwidth, it's at this chip level. So this is the kind of bandwidth that you can expect out of each memory chip. So the latest that you see here, right, is like 84 gigabytes per second. And then you have a system bandwidth. So you are looking at the system as a whole, GPU plus 12 dice. So you multiply by 12 because you have 12 memories here, each of it having its own I/O interfacing with the GPU. So you can expect greater than 1 terabyte per second to be sent out to your GPU. So that's the kind of information that it's being that you can actually process in your GPU. And next comes HBM. So HBM is, again, as I said, is an emerging memory which caters to the generative AI applications and something which actually needs large amount of data. So HBM stands for high bandwidth memory. So this is how it's typically constructed. So you have a stack of memory devices. This is, each one is a DRAM chip here, and you have these yellow lines that you see here. These are the through silicon vias. So you have through silicon vias through the DRAM all the way up here, and this is your GPU, which is housed right next to it. And we have this on a silicon interposer, which will get eventually connected to a substrate. So if this is the 3D view of it again. So you have your SoC or GPU sitting here, and each tower that you see here is a HBM DRAM chip. So this tower is what you would see here. And you have multiple such HBM DRAMs, and each HBM DRAM actually supports a very large amount of data, which I'll show the kind of things that we have here. So in a sense, you can support multiple terabytes of data being flushed into the GPU every second. So yeah, we have seen the compute side, we have seen the laptop, just get this, and we have also seen how a typical GPU system is constructed. And this is the HBM. As I said, you have a stack here. It's a multi-high DRAM stack. So typically the configurations are 2, 4, 8, and these days we are also talking about 12 high stack. It essentially means you'll stack 12 DRAM chips one over the other. So this is how it's stacked, and blown up version of that is shown over there. So you have a chip and you just flip it and paste it to the substrate and then start constructing it that way. So your front side or your topmost metallization would be the one which is sitting on your substrate. And then you have your through silicon, which is via, which is your copper there, connecting from the bottom die to the top, and then it goes on and to the next one. And this is a HBM system. Now, just to summarize what we have seen so far, we have seen a compute domain wherein it's typically a high density mobile, and DDR is the terminology that is used in the computing world. DDR4, DDR5 are two different generations, and then you have different device configurations, 8 GB, 12 GB, 16 GB, and so on and so forth. And then comes mobile. As I said, mobile, the key driver here is low power. You need to ensure that the power dissipated by the DRAM is kept on the lower side. we targeted for mobile and automotive applications, and HBM and graphics on the other side is targeted for artificial intelligence, generative artificial intelligence, virtual reality, augmented reality, gaming. So that's the sector that it caters to, and the IO requirement here are much more. So if you look at it, right, so we talked about the prefetch earlier. So prefetch for every command, so RW is the read write command. So for every command that you give, a read or a write, in DDR4 and DDR5 we fetch about 128 bits or 256 bits as is the architecture, and that's predominantly true for LPDRAM and HBDRAM to some extent. But the key differentiator is your external DQs. So we said it's by 4 or by 8 or by 16 in your computing world. LPDDR still supports by 16, but if you look at the HBM, it's 1024, which essentially means you can have a very wide IO interfacing with your GPU, and that is what gives you an enormous advantage of pumping in a lot of data into your GPUs. So I think we have seen the overall context of where this DRAM fits in terms of products. Now let's get into a bit more on the technical aspects of building this DRAM chip. What goes into building this DRAM chip? So yeah, if you look at the DRAM chip in itself, right? So as we talked about different high speed requirements. So there is always a requirement for improving the speed. So we talked about starting with say 2 Gbps, 4 Gbps. Currently we are at LPDDR5, which is like 8.5 Gbps, and going forward it will be 10, 12 and so on and so forth. So there is always an increasing appetite for performance and bandwidth. And then we also talked about low power. So low power for longer battery life, and low cost of course is always our driver. And also there are application specific features that gets incorporated into such systems, and we want to pack as much memory as we could in a given silicon footprint. So that's always the requirement. Now what does this translate to for engineers like us? So there's a lot of digital design that goes into this, analog design, IO design, memory array design, and of course package and module design as well. So let's see where each of these get introduced or used, right, in the overall thing. So this is the typical block diagram of a memory. So DRAM memory, by the way. So it's organized as multiple banks, and each bank houses multiple rows and columns of memory. So since we have multiple rows and multiple columns, you need to have a row address and a column address decoder. So you have a row decoder here and you have a column decoder here, and you fetch data, the data comes out, and that data comes through a sense amplifier and gets you got a rail to rail output, and then goes through control logic and comes out to your read path. So if you are reading some data out, this is the path that it takes. You have the read data coming out, gets buzzed, and then you have a driver which can drive this data outside off chip, and then finally comes out as the DQ bus, and this DQ bus is what interfaces with your CPU. So we have seen this DQ. Now the other pins, right, we also have reset, clock, clock enable, chip select, command address, and on-die termination. So let's look at a bit more details of each of these, right. So where does each of these fit in? So once you have once you're interfacing this with the CPU, what does that CPU do? It will, suppose I want to read something, some memory data, it will give you a read command. The way it does is it will put the command information and also the address information onto this CS and CA, these pins. So you need to have address latching mechanism and some control logic that goes along with it, which can eventually translate whatever has been captured into a proper row address and a column address. So all that needs a lot of digital circuitry. And then I also talked about using DLL for clock synchronization. So that again is something that we would be using it for. And then there is mode registers. So we could operate the DRAM in multiple different modes, and there are different frequencies that you would need to be operating it for. Let's take a real time example, right. We could use our mobile phone for just scrolling or for watching a video or for gaming, right? And each of this needs different amount of DRAM data and at different speeds as well. So if you're just scrolling or if you're just turning on your mobile phone and just keeping it stagnant, right, then there's not much of data transfer that's happening. So you could operate your DRAM at lower speeds, as opposed to running a high bandwidth gaming application, right? If you're actually playing a game, it needs very fast picture transfers, and that needs a huge amount of data to be transferred at a really high speed as well. So there you would need to operate your DRAM at a higher speed. So if you're operating your DRAM at a higher speed versus your DRAM at lower speed, right, you could actually do power optimization within the chip. So you essentially configure your DRAM in such a way that, okay, if you are doing a high speed, this is the kind of blocks that I'll enable, and if you're doing a low speed operation, you have a different set of things to be enabled. And mode registers comes in handy to ensure that you have all those things captured in a proper manner. So you'll have your frequency set point. Let's say you're operating it at 200 megahertz. So all the 200 megahertz related information is captured in one particular mode register, and you'll have a different frequency set point, say 2 gigahertz or 4 gigahertz, whatever, right? So that is a different frequency set point that is captured in a different thing. So all that things that are specific to DRAM handling and DRAM operation are captured in mode register, and that by definition is a register, and there is some amount of logic involved there as well. And then we also need to train this memory. So as I said, we need to interface this with a CPU, and the CPU resides somewhere else. And now you have clock and data coming into your system, and you need to ensure that with that clock you are able to sample the data properly. So what if there is a skew between your data coming in and your clock, right? You need to somehow ensure that whatever at the flop which you have built inside your DRAM chip, you have a sufficient setup and hold margin. So to ensure that, we have something called training, and you have training for both DQ as well as command. So you have a command address bus coming in, and you also have DQ bus. DQ is a data bus, and DQ, by the way, is the bidirectional. You'll use it for read as well as write. And then we also have DFT incorporated, so fuses and redundancy. So we are excuse me, we are building such a large memory system, right, running into gigabits of memory. What if a row goes bad, or what if a column goes bad? We need to have a mechanism to repair that out, and that is where redundancy comes in. So we'll inherently build some additional redundancy into the system, so that once we do a package level check of the entire memory, if you figure out that one particular row has or one particular column has gone bad, you will replace that with a redundant either row or column. And similarly, ECC is built in. So suppose if we have ensured that we have at the time of packaging, right, when we are handing it over to the customer, everything is working perfectly. But on field, there could be some glitches wherein you could just start seeing single bit fails. So how do you address those, right? So to address those, you would need to have error correction codes. So data doesn't come out as is, but you will take it through an ECC engine, so that if there are any single bit fails, those get corrected out. So all that needs a lot of digital design that goes into this. And similarly, there is a lot of analog thing that goes into the system as well. We can start with a simple DRAM operation, right? It's a 1T 1C cell. And this 1T 1C, suppose if we are operating at a VDD domain, right? Your gate voltage of this NMOS can't be VDD if you want to operate your cell at VDD. It has to be slightly above that, because you need to overcome the threshold voltage of the NMOS transistor. So you need to have a mechanism to boost the voltage from your VDD domain. So you need to have charge pumps, and the charge pumps by construct, right, would need a band gap reference to be pumped in, and then you will also need voltage regulators. So if you look at the overall construction, we would have multiple internal supplies within a DRAM chip, more than 10 easily. And we also need a temperature sensor. Why a temperature sensor is needed? Because as I said, DRAM is dynamic in nature, wherein the charge would leak out as a function of time. And this charge leakage is strongly dependent on temperature. So if you are operating it at 25 degrees as opposed to 125 degrees centigrade, right, you have significant difference in the leakage currents. So 125 degrees centigrade operation would have much higher leakage as opposed to 25 degrees centigrade. So the chip should somehow know that it's operating at a higher temperature and start refreshing at a faster rate. So that's the need of temperature sensor, and then we also have clock handling. Where we talked about DLL in the previous slide. DLL or a PLL would be needed, and there's a lot of analog circuitry that goes in there. And the data drivers that we have, right? So these are, it's like a high speed interface. We're talking about 8.5 Gbps, 9.6 Gbps and so on and so forth. And the way it's constructed, you don't have a conventional CMOS logic there, but instead you will have a differential current mode logic, so that you can support those high speeds. And we also need to have reference generators for those current mode logics. So it's like a diff amp, wherein you will have a VREF both for the DQ as well as for the command, and that VREF has to be generated internally, and that again is an analog block. So there is a lot of analog that is built into the system. And then we also have a memory array. So as I said, right, it's organized as multiple banks here, and you have different row addresses and column address things that are interfacing your bank. So all that is part of your memory array. And then I/O design. So all the I/O pins, right, that you have here, and this is something that I didn't talk about. This is the ZQ calibration. So as I said, we are talking about very high speeds, say 5 gigabits per second to 10 gigabits per second. So for these rates, right, you just can't have an open-ended or open drain architecture. So that will result in a lot of crosstalk and intersymbol interference. So typically we will have this terminated so that reflections are avoided. So when you want to have this terminated, you need to have a proper termination resistance as well, and ZQ will determine what is the appropriate termination that you would have in your system, and all that is part of your I/O design. And then we have now built the system. Now comes the package and module. So this also is a study in itself. So once you are configured with your DRAM die, you need to ensure that at the system level also your intersymbol interference, your signal integrity is taken care of. So there's a lot of engineering that goes into making this PCBs work at such high speeds. So let me just focus on DRAM cell a bit. So we talked about 1T 1C cell. So that's the primitive cell that we use for DRAM construction. So here we have your word line and your digit line. So these are the two most important knobs for accessing your bit information. And by the way, the bit is stored as charge or voltage on the storage capacitor. So other end of it is typically grounded, or you could have a reference voltage here. So word line is the one which is accessed through your row decoding, and then through the column decoding you will have the digit line accessed. I talked about word line voltage being higher. So as I said, it's the NMOS transistor based DRAM cell that we typically have. So if you want to operate this at VDD levels, your word line voltage has to be much higher than that. And you would typically stack multiple of those in a row, and the row would span say 1024 cells or 2048 cells. And if you're talking about that high thing, right, running on a poly, you would have significant amount of resistance there. So in order to ensure that you can meet your memory speeds, it's not good enough if you just have 1 VT above VDD. You need much higher voltage there so that your drive strength and the last cell also gets appropriate drive strength. And we talked about this before. DRAM is dynamic in nature, and there is charge leakage that's involved. So there are multiple leakage mechanisms. So the figure on the right shows a typical cross section of a DRAM cell. So this is your storage cap built in the middle of the line. So this is where your transistor resides. Then you start your middle of the line, and then this is the back end of the line. So this is how a capacitor is constructed here, and then that gets interfaced with your transistor. So this is your 1T 1C cell, and there are multiple leakage mechanisms, as I said. So it could be your transistors subthreshold leakage, PN junction leakage, cell to cell leakage, and then through the dielectric of the storage capacitor. So there are multiple paths for the charge to leak out, and at the end of the day you need to ensure that you are going to refresh it back in periodic intervals so that the charge is retained as long as you want it to be. And typical Tref is 64 milliseconds. So Tref is the refresh time, refresh spec. So within 64 milliseconds you should be refreshing the data, and that's how we construct the DRAM. Let's look at how we access a particular cell. So here this is your cell, C cell, and you have multiple such cells tied to a digit line. So if you have, if you're aware of typical how a memory is constructed, you have multiple rows and multiple columns. So along a column, you'll have multiple rows, and each row will have one cell attached to it. So you'll, at the end of the day, you'll have some amount of digit line capacitance associated with the digit line as well. So if you're accessing a cell here, it's like closing the switch here. This is your access transistor. It's we are mimicking the functionality of switch access transistor through using a switch here. So if you're going to supply a VCCP voltage, the switch gets turned on, and you're now going to dump this charge onto your digit line, or dump the charge from your C digit onto your C cell, as is the case, whether you're reading or writing information, and whether the cell is storing 0 or 1. So suppose say we have a cell that's storing a 1, and then the C digit is pre-charged to a certain voltage. So the way it works is, when you access this transistor, there is some amount of charge distribution that happens. So if you have stored a 1 here, and if you have stored a 0.5, which is VDD by 2 here, right, based on the ratios of these two capacitance, you'll have some amount of voltage bump on this line. So if you work out the math, if you take an example, let's say C cell is 25 femtofarad and C digit is 100 femtofarad, and if you want to store a 1 on it, which is in our case suppose is 1.5 volt, and the other side of the capacitor, which is your reference voltage, is 0.75, then once you turn on the cell, the voltage that you would see is 0.9 volt, and it's not the complete 1.5 volt. This is because of the capacitive divider network that we have there. So what the point that I'm trying to drive here is, when you are accessing the cell, you will not get the complete rail to rail information on your digit line. It's just a delta voltage that gets developed. It either gets developed or gets shrunk. So if it's a 1, there's a bump, a positive bump, and if it's 0, there's a negative bump from your reference voltage. So if your reference is 0.75, you see only 150 millivolts of swing, either positive or negative, and this has to be translated to our rail to rail eventually, and that's where you would use the sense amplifier. So suppose if we are accessing a 1, at the beginning of this operation, in this sense amplifier, you will have 0.75, 0.75 on either side, and once you have accessed a 1, let's say digit goes from 0.75 to 0.9 volt. Now you will have to sense this differential, and that is done through this cross coupled sense amplifier. You get a rail to rail data, and that is eventually fed out all the way to your DQ. And the way you organize this sense amplifiers is like this. So you have memories here, and each vertical line here represents a row, and the horizontal line represents a column. So you have sense amplifiers on either side. So whenever you are accessing a particular row and a particular digit line, so the data from this gets altered. So if it was 0.75 earlier, it gets altered to 0.9 now, and the sense amp's other input comes from the other bank, which is not accessed. So if you are accessing a row here, all the rows in this particular bank are inactive. So there is no perturbation on this digit line. So this will stay put at 0.75 volt, and then you will have a differential built at this sense amplifier, and that will be read out. Now let's see how a typical DRAM is constructed. So you have multiple banks. So each one is at 128 megabit subarray that we are talking about, and then you create openings here for your sense amps to reside. So those are the purple ones are going to be your sections, and then you have your sense amp regions, and then between banks is where you have your row decodes, and then below the sense amplifier at the bottom of the bank is where you have your column decodes. So the column in this particular diagram, the column lines run vertically and the word lines run horizontally, and you have all your pads and bank logic, all your necessary interface happening here. This is again an example of typical DRAM floor planning. So you have your rows running vertically here and the columns running horizontally here, and sense amps are sitting in between. And whenever you are activating a row in one particular bank, you don't do that on the other bank, so that the digit line that's tied to the sense amp could act as a reference. This is a read data path. So you have your word line tied to your bit cell. So this is the innermost portion of your DRAM. Then we have seen the sense amplifier. You get the data out through the sense amplifier, and then you have a column select which will transfer this data to an IO line. And as I said, we don't restrict ourselves to just one bit capture, we do that for multiple bits. So, along with this you have multiple other cells that are getting turned on simultaneously. So, you have a parallel stream of data coming in to your which are channeling all the way up to your IO to your DQ, and eventually whatever 8-bit or 16-bit prefetch that you do is transmitted serially onto your IO pin. So, the parallel to serial conversion happens here. So, till here you have a parallel data stream coming in here, and then you convert these 2 bits into a serial stream, and then you use the IO driver to drive it out of your chip. And this is a voltage waveform for a read operation. So, you have both the bitline true and bitline complement or bitline bar equilibrated at VCC by 2, as it's 0.75 in the previous example. Then once you give a read operation and once you turn on the word line, so the blue here represents the word line. Once the word line is turned on, you have charge dumped onto one of the bit lines, which is bitline 2 here. So, you see from 0.75 there is small amount of voltage bump that you would see. Now, this has to be resolved all the way to the rail, and for that to happen you enable your sense amplifier. So, the sense amplifier you saw is a cross coupled structure. You had NMOS cross coupled and a PMOS cross coupled. So, here it is shown in a way therein you enable the NMOS cross coupled first. So, the one the NMOS which has a higher gate overdrive pulls the other bit line low. So, this goes low and the other is almost tapered, and then you come back and turn the PMOS cross couple as well. So, that is when your thing which is residing currently close to VCC by 2 will go all the way up, and now you have a rail to rail information which will eventually be fed out to the other stages. Same is true for the right paths, it is just opposite. So, here you have data coming in from the external world into your DQ, it is going to be a serial data stream here, and then you will have a serial to parallel interface block, wherein you will convert that into a parallel 16-bit stream or 8-bit stream, and then that goes all the way to your cell, and I will skip this in the interest of time. So, let us look at the data sheets, right, what is typically captured in a LPDDR4 data sheet. So, this is if you look at here, we have 3 different supplies, VDD1, VDD2 and VDDQ. So, VDD1 is a higher in number, so it is typically higher in terms of absolute value I mean. So, the nominal value if you see it is 1.8 volt, and VDD2 is your core supply. So, all your memory cells operate on VDD2 supply, and VDDQ is the IO supply. So, this is what the CPU interfaces with. So, the DQ runs with this supply, whereas the VDD2 is what you would be using for your internal core memory core operation, and VDD1 is used for all analog generation, supply generations. As I said, we need a much higher gate overdrive for the DRAM bit cell to operate. So, even though the cell that is storing 1 volt, you would need say 1.5 or 2 volt on the gate, and that is generated using this VDD1 supply. So, those are the 3 primary supplies, and then of course, you will have VSS ground, and we have a 16-bit architecture here, and there are 8 banks here and single data rate command. So, if you look at this now, right, you would at least you would have got an overview. It is may not look so overwhelming as it would have if you are looking at it for the first time. So, we have covered most of the topics here. So, it gives you a gist of what is it that goes in building a memory system. Now, coming to the key features of an LPDDR4. LPDDR4 is by the way the low power DDR current generation. There are quite a few chips with LPDDR5 as well. So, it is like one generation before or one generation current generation, as you could say. We saw single channel versus dual channel earlier. So, if you have a 64-bit data, if you are talking about a CPU's domain system, you have a 64-bit data, then you need to have 8 bits of 8 DRAM chips that you need to be interfacing it with. And suppose say your system can support 128 bit. So, instead of a 64 bit, it can support a 128 bit. So, then you can enable multiple channels in your DRAM cell, so that you can have 2 parallel data outs now. So, instead of 16 DQs, you can have 32 DQs come out of this using 2 different channels. So, LPDDR4 enables this. And then we have multiple internal supplies, we have data bus inversion scheme. So, data bus inversion, right. So, this is I will talk about it in subsequent slide what it actually means. ODT is on die termination. We talked about high speed interfaces here running up to gigabits of transfer speeds. So, when we are doing data speed transfers at that high rate, you need to have proper terminations, and ODT is used for that. And LVSTL is low voltage swing terminator logic. So, instead of open drain logic, we have something called low voltage swing terminator logic. I will talk about this also in the subsequent slide. And IO termination is VSSQ based, and operating voltage is 1.1, and burst length we have seen this is like a prefetch. So, are we prefetching 8 bit or 16 bit or 32 bit? So, this talks about that. And then we have 16 DQs. So, if you are doing a 32 bit prefetch or a 16 bit prefetch, so it will talk about how many bits of data are you prefetching for every command. Right leveling is again part of your training thing. So, as I said, when you are interfacing a DRAM chip to an SOC, the clock comes in and also the data comes in. Now, it is our responsibility to latch the data at the clock edge, and if there is a skew between those, right, you will be able to, you will not be able to capture it properly. So, internally you will have to ensure that the clock and the data comes such a way that the clock comes right in the middle of your data eye. So, that is done through right leveling schemes. And SDR stands for single data rate. So, we have 6 pin command address scheme, and we do not need a DLL for LPDDR because the system is very small. So, the footprint, right, overall footprint is going to be much smaller compared to your DIMM module. So, this goes into your mobile. So, you do not have much area there, much room to have SOC and the memory space far apart. So, it is more or less packed one over the other or right next to each other. So, the interconnect delay between your SOC and memory is going to be very limited here. So, you can afford not to have a DLL or a PLL here. So, this is the dual channel system. So, the right figure, right, this is the conventional architecture wherein you have your command address coming in here and you have your DQs here going out to your system. So, this is all your memory banks. In this architecture, right, whatever, if you have a data here versus data here, everything has to come out through this. Now, a dual channel, that the benefit that you get is you can actually break it open, and then half of the banks can be supported using this DQ and the rest half using the other DQ. So, this way now you are actually cutting short your interconnect length from the bank to the DQ. So, that enables higher speed of operation as well. LVSTL, the low voltage swing terminator logic, right. So, conventionally this is what we have been doing, it is in a high speed unterminated logic. So, when you are transferring data on your DQs, this is the kind of swing that you would see, it will go from VDDQ all the way to 0. But this cannot support the kind of high speeds that we would like to it to support, right. So, going forward the LP restricted itself to something called low voltage swing terminator logic. So, wherein you do not have VDDQ all the way here, but instead it will be VDD by itself by a factor. It could be a 2.5 or 3 based on what the system is, right. So, earlier systems go all the way to say 1.1, 1.2 volt here. Now, this is how it is. So, your DQ's voltage swing is restricted to very minimal amount. So, that way you do not have to have a very high swing here, and that helps in lowering the power requirements, right. Low power is what you want to have. So, you do not swing so much. But this will not hold true for a DIMM module. DIMM module you need to support very high data lengths running into centimeters. So, if you are going with this architecture, you will end up with data eye closures. So, there you would need to still have VDDQ, but you will use terminations, but you need to have VDDQ there, which is 1.1 volt, whereas VDDQ here will be much lower. I will skip this. Yeah, what I wanted to just say is multiple commands that we have in a DRAM chip, right. Activate is row activate, and then you have write or a read command, and then cas is your column address command, then pre-charge and multipurpose command and deselect. So, this is in essence the various commands that it caters to. This is much smaller compared to what you would see in a, say a microprocessor, right, which has a huge set of commands. This is much smaller, but still nevertheless it has its own set of challenges in terms of building the system and making it work at such high speeds. Let's get this. So, yeah, this is a typical timing diagram that you would have. So, this is your command address bus, this is your row address, this is your bank address that you are feeding in, and then this is your activate. This is the command. Oops, sorry about that. By activate we mean a row activate. So, you are doing a row activate, which is a multi-cycle command here. So, this is your clock cycles. The row address, if it's a big chip, 8 gig or 16 gig, you might need to have 12 bits of row address or 13 bits of row address being transferred. And as I said, we just have 6 bits of C command address that are available. So, you will not be able to transfer the entire row address in one cycle. So, you need multiple cycles, and that is what is shown here. So, you are transferring it over 4 different cycles here, and this is row opening for one particular bank, and similarly after some time you can do a row opening for a different bank. And so, the row to row operation is TRRD, and there are multiple other such timing parameters that you would be interested in sort of DRAM world. I talked about this frequency set point. So, if for example, if you are doing sending out an SMS versus taking a call, attending a call, right, those are all typically a low frequency operations as opposed to doing a video recording or playing a 3D game. So, those are high frequency. So, you would have 2 different frequency set points, and that is done through mode registers, and we talked about mode registers as being part of your digital design framework there. So, this is where it all ties down to. And data bus inversion. So, this is again a low power feature. So, if you are transferring bits, ours is the LP is a VSS terminator logic. So, when you say VSS terminator logic, when you are transferring a 0, you actually do not burn power, and when you are transferring a 1, you will have a voltage divider, and that is when you burn power. So, if you are transferring a stream of zeros, there is nothing on the VDDQ that you are burning. It is actually idle, I would say. So, now let us say we are sending data streams from your CPU to the memory, and you have a stream of 1 and stream of zeros. Now, we are just trying to take advantage of the fact that if you are transmitting more zeros, you are not burning power. So, the way we do that is you count the number of ones that you will have in your stream, and if that ones exceed 1/2 of your data bits, then you actually use this DBI bit to tell the DRAM saying that, okay, I am actually sending out inverted data pattern to you. Internally, you will have to invert the data pattern. So, instead of sending out, suppose we are sending 1 1 1 1, if you send out 1 1 1 1 as is, you are going to burn more power. Instead, we will send 0 0 0 0 and use one more DBI bit and say that the data stream is inverted, and internally DRAM captures all the 5 bits along with the DBI bit, right, and it will see, okay, the DBI is 1, which essentially means the data bit is inverted. It will do a data inversion internally and use that for data storage. So, that is the DBI scheme. We talked about error correction code. So, you need this on field. So, if there is a 1 bit error that happens on field, right, there has to be a mechanism to correct it. Otherwise, our mobile phones does not work anymore, right, if there are on and off errors. So, ECC comes in handy there, and we also have something called post package repair. So, there is a mechanism wherein even after packaging, if you feel that there is a particular row that is failing and you need to repair that out, there is a mechanism to have that done as well. We talked about LPDDR4. So, what are the enhancements that you see in LPDDR5? So, LPDDR5, the latest phones, smartphones that you see, right, comes with LPDDR5, the premium phones that you will have. So, here the bank architecture, the architecture diagram that I showed earlier had multiple banks, maybe 8 banks, 12 banks, 16 banks. So, here the architecture, there is a slight modification that is done here. So, instead of arranging all as single group of banks, you have multiple groups now. So, you will have 4 banks in one bank group, and then this bank group versus next bank group, if you are doing an access, right, you will have a different timing versus accessing all of them simultaneously. So that way you are able to improve on the speed here. The other feature that was brought in is called dynamic voltage and frequency scaling. Probably if you have gone through a digital design course, right, you would have come across this term called dynamic voltage and frequency scaling. So that is something that you will actually see it happen in the DRAM chip. So if you see that for a significant portion of time DRAM is going to be used in a low power mode or a low frequency mode, you can actually bring down the voltage for some portions of it, so that the effective power that it burns out will be lowered. Next is NT-ODT, non-target on-die termination. I will talk about it using a slide. Right X function, I have a slide for that as well, and speeds have increased. The LPDDR4 catered up to 4.2 Gbps. This goes up to 6.4 Gbps, and then we have LP5X, which is 8.5 Gbps. And the earlier one supported 2 frequency set points, this supports 3 frequency set points. So this is the bank architecture that I was talking about. So the LPDDR4 had just one grouping of all banks together. So suppose you are accessing something from this bank versus this bank. The data, you are limited by this transmit time now. Everything is limited by the farthest one. But as opposed to that one, right, wherein you have grouped them together, if you are accessing something within this bank versus this bank, right, all your data buses are limited to this. So you will actually be able to support a higher speed here. And you can take a speed hit when you are moving from one bank group to the other bank group. Dynamic voltage and frequency scaling. So this is your bit cell. So bit cell always operates on a VDD2H, which is your 1.1 volt supply that I talked about. And then this is the data path. So once the data has been read out, you take it through the data path and go take it to the IO driver eventually. And in the data path is where you do all your optimization. So you can either feed in a VDD2H or a VDD2L, which is a lower supply, 0.9 volt, based on frequency of operation. So if you feel that for the next few microseconds, your DRAM is going to be operated on a low frequency mode, then you switch to this low frequency mode and turn down the supply from VDD to H to VDD to L. So that way all your data path will be operating on a lower supply, burning lower power. And then IO driver, the IO driver makes VDD to H and VDD to Q, and there is no voltage scaling here. NT-ODT, this is the non-targeted ODT. So as I said, on-die termination is needed for supporting high speed of operation. So let's take this example. This is your driver, this is the controller or CPU driving some data into your memory. You are doing a write operation, and this is your memory. These are two different memory chips. So this is the non-targeted rank, and this is the targeted rank. If you remember at the start of this talk, right, we talked about two different ranks being enabled on a DIMM module. So in order to improve your memory capacity, we can have multiple ranks. So in such a scenario where you have multiple ranks, you have the same data bus tied to both the ranks. And now this data, this is the targeted rank. You need this data to go into this chip, DRAM chip. You don't need this data to go into this chip. But this chip also resides on the same DIMM module. Now whatever has been transmitted from here goes to both the places now, and since this is your non-targeted, right, you will have this chip in the off mode, and once it is off, it is like a floating line, and this data comes in at a speed of say 4 gigabits per second or 8 gigabits per second, and that speed you start seeing reflections, and once this gets reflected, that goes back again into this path, since they are all on the same electrical line. And once that happens, right, your data I, the data opening will be cut short. So this is what you would eventually end up in a conventional case. So what is shown here is a data I, wherein you are overlapping multiple ones and zeros over a large time window captured in a unit interval of time. So this is how it is. Now when you enable this NT-ODT, so what happens is you will have this, even though the chip is off, you will ensure that the time termination is properly turned on. So what comes in just gets terminated here. So there will be no reflections coming out of this as opposed to what happened here. So because of that, you will not see noise getting injected into this system, and your data I improves. So what was just 0.4 now you see an opening of 0.53. UI is unit interval of time. So if it is 100 picoseconds, say, just 40 picoseconds of opening is what you had initially, but now it will be 53 picoseconds. So you have a wider window for data to be captured properly. So this is something that is employed in LPDDR5. Write text feature. So if you know that there is a particular data stream that you want to write to a memory, a fixed pattern, say all zeros. So then you don't necessarily have to turn on all the DQ and the clock from your controller. Instead, you can use this command and say that, okay, I am going to write only zeros for the next 3 commands, and then just feeding the command. So that way DRAM internally knows that, okay, I need to use this known data stream, which is already captured internally in one of its mode registers, and use that data to write into the DRAM. So this is again a low power feature. If you know what data stream it's going to be written into, then you can use this feature to cut down on the IO power. Now I will come to the last topic, technology scaling. So to the left, this is the cell capacitance. So this is the different technologies, right? You might have heard of CMOS technology, 65 nanometer, 45 nanometer, 10 nanometer, 7 nanometer, and it's a single digit now, 3 nanometer and all. So this, in the DRAM world, this is the different technology nodes that we are traversing, and we are currently at 1 alpha or 1 beta node, and 1 gamma is what will be next, right? So this is, with technology, you start shrinking the dimensions. So that is what is done in conventional CMOS world as well. So when you progress from 65 nanometer to 45 nanometer, all your gate lengths would shrink. And same is true here as well. So here we are talking about DRAM cell, which is 1T, 1C. So the transistor cell capacitance is going to be shrunk. So what was 20 femtofarad earlier is going to be less than 10 femtofarad in 1X node, and at 1Y node it will be even further lower. So what does this translates to, right? So you have a lower capacitance now, essentially means when you are interfacing that with your digit line, there will be a lower voltage that gets developed onto your digit line. So earlier, in the earlier example, we had 150 millivolts of data information being fed to your sense amplifier. Now it could just be, say, 100 millivolts or even less, 75 millivolts. So your sense amplifier now has to resolve that smaller amount of delta. So it essentially translates to sense amp margins. So sense amp margin is going to get lower and lower with technology. And then there is one other downside to having lower capacitance is essentially Q is CV, right? Q is equal to CV, and we are scaling down the capacitance, which essentially means the amount of charge that you are putting on your capacitance is also getting reduced. And now since the leakage is going to remain more or less same, you are going to leak out faster. The amount of charge, right, that component is going to get leaked out faster, which essentially means you need to ensure that you are able to refresh it at a faster pace. Refreshing faster means again more power. So that's another challenge that we have to face. And there is one other concept called row hammer. So suppose say you have a DRAM chip and you are repeatedly targeting one particular row and accessing data from the same row time and again, like 100 times, 1000 times, right? When you start doing this, the way DRAM is constructed, within the next 20 or 30 nanometer space, you have your next row. So whenever you are repeatedly accessing this, so what are you doing is you are creating a VCCP level of voltage on your cell, gate voltage, and then bringing it down. So a repeated electrostatic field interventions there will cause disturbances on the data stored on the neighboring cells. So that is what is shown here in the physical thing. So if you repeatedly take it to VCCP level and bring it down, after some times you start influencing the data stored in the neighboring cells as well. So the charge here starts leaking out. So even though you are not reading out data from the neighboring cell, just because you are reading a cell from the row -1, your row, the actual row starts getting affected. And you need to now somehow ensure that that row which is getting affected is also refreshed. So that's called a row hammer refresh. So the row hammer refresh mechanisms become even more complex with scaling of the technology. So that has to be taken care of. So one way that you can address that is by having a higher VT so that you don't tend to lose charge. But the moment you have higher VT, you will start hitting your speed. The performance is a challenge. So there's a trade-off there. And then we talked about retention times. The retention time as a function of temperature as well. So if you are doing a room temperature operation versus a high temperature operation, your refresh rates have to be much higher at higher temperature. So that again is a challenge, and once the cell is getting scaled, it's even more challenging. We also talked about sense margin being lost. So this chart shows the amount of sense margin that you have. So this is on a scale of 0 to 1 volt. So this is the 0 margin that you have, and this is the 1 margin. What I mean by 0 margin and 1 margin is, on the cell you are typically storing either a 0 or a 1. So you can afford this much amount of noise on the cell and still be able to reliably read out a 0. And similarly, you can tolerate this much amount of noise on the cell when it is storing a 1. So it need not store 1, it can store say 0.95 volt as well, and you will still be able to read a 1. And similarly, you need not store a perfect 0, you can store 0.1 and still be reading out a 0. But that will start getting shrunk once you are progressing from one technology node to other technology node, because you have higher and higher variations that come into picture. So this will get shrunk, and then there is a circuit technique that is employed of late, which is called VT offset compensated sense amplifier. So you might have heard of process variation. So when you move from one technology node to the other technology node, right, you have process variation being a significant factor in the most advanced technology nodes. So to cater to that, there is a circuit technique that is employed wherein you somehow nullify the VT variation component here. So with that, you are actually able to improve the margin. So what was 0.1 probably gets improved to 0.2, and what was 0.9 probably gets improved to 0.8. So that way you are building in more reliability into your system, and that is at the circuit level. Now at the device level, right? So we have migrated from a conventional Scion device to a high K metal gate device. So with this, your I-off performance has increased and also I-on performance. So for a same I-off, you have a 58% improved I-on, and similarly for the same okay, this is for the NMOS and PMOS, that's very shocking. So if you translate this chart to otherwise also, you will see a similar performance. For the same I-on, you will see a better I-off. And not just the drive strength, your VT mismatch also improves, and that also translates to your better sense margining. So where are we on the current trend, right? So I talked about LPDDR4 and LPDDR5. Going forward, we will see LPDDR6, and that's on the low power front. And on the graphics front, I showed a chart where we said GDDR5 and 6, 6X. So we have started looking at GDDR7 as well. So this is a IEEE paper from Samsung on GDDR7. And on the HBM front, we are currently at HBM3. Going forward, it will be HBM4, HBM4E, and so on and so forth. And all this is so far planar. By planar, I mean you have 1T, 1C being constructed on one level of silicon. But going forward, there is a lot of effort on creating this as a 3D device, not the 3D stacking of HBM. So HBM 3D stacking is through silicon vias. So we have a DRAM chip, and you have another DRAM chip, and these two talk through silicon vias. The 3D that this paper talks about is trying to create 3D layers of DRAM cells within the same silicon chip. So within the same silicon footprint, instead of supporting say 8 GB of memory, if you now support say 4 layers, you can get 32 GB of memory within the same silicon footprint. That's really a commendable effort if it really happens through. And this would also be an important game changer for generative AI and data intensive applications. So on the 3D front, there's a lot of effort, a lot of research happening from various players, various companies, right? Micron being one of them. So this is, you have Samsung, AMD, Kioxia. So each company is investing a lot into their 3D technology, and you see that we are currently in year 2024, we have a 3D NAND. So 3D NAND, by the way, is already existing. So when you talk about 3D NAND, you have NAND cells with 232 layers or 276 layers currently available in the market. And going forward, we might have 3D DRAM as well. So So this is existing, and beyond 300 layers is something in pursuit. And then, yeah, so these are hybrid bonding, and this is 3D or 2D, 2.5 TSP enabled. So when we talk about hybrid bonding, we are talking about having an interface die and DRAM die as two separate entities which are getting hybrid bonded. And TSP, as I said, is like a monolithic same die, but replicated multiple times, and they are talking through TSPs. So that's all I wanted to share with you all today. So DRAM, as you have seen so far, it, yeah, thank you for that. Multiple applications, AI, VR, gaming, graphics, and HBM. And if you look at where a design engineer would fit in, right, you'll see that the DRAM design spans multiple domains: memory array, digital design, analog design, IO design, high-speed interface design, package design, module design, thermal design, right? There are multiple opportunities that exist for VLSI designers. And it also talked about technology scaling and design architecture improvements which have helped so far, and this will continue to happen for us to enable the next generation DRAM chips. And HBM and 3D DRAM are the most emerging ones and which have high potential going forward for enabling generative AI. Yeah, thank you all for your attention.
Hello, sir.
Yeah.
Sir, it seems that DRAM design is mostly analog IC. But what is the role of digital there?
Role of digital, as I said, there are multiple places where you need to have digital thing here. So one is row address decoding, column address decoding, and your data path. So data path, right? Once you fetch the data from your DRAM cell, you need to take it through the sense amplifier, which is like a mixed signal block, mixed mode block, and then once it comes out of that block, it has to reach your DQ driver. The DQ driver is again going to be analog, but this path all the way from your sense amplifier till it reaches that DQ block, right, wherein you go from one bank to the other, and then do if you are doing a read operation, you need to do a parallelization to serialization, right, parallel to serial conversion, and you also need to have FIFO. You need to support multiple read operations in parallel from this CPU. So CPU can keep firing read operations every couple of nanoseconds. So internally you may not be able to have data being read out at that high speed. So you need to have a mechanism wherein you can store it locally and then start streaming out serially. So you need to have that FIFO built in. All that FIFO is your digital logic. Your high speed interface is a digital logic. Your row address column address decoding is digital logic, your command address decoding is digital logic, your mode registers is digital, some amount of digital goes into your delay log loop as well. So yeah, there's a lot of digital that goes into the system.
Okay. Are there any analog portion in SRAM?
Analog portion in SRAM, again, if you are using two different supplies, right, for your core versus your peripheral, to realize that additional core supply, you would need to have band gap voltage and a voltage regulator. So that's an analog supply. And then of late, you started using this, what's this called, write assist circuitry, wherein you use negative bit line voltages. So to realize this negative bit line, you again need to have negative regulators or negative charge pumps. So that again is an analog block. So sensamp to some extent is a mixed block, but apart from sensamp, you have this voltage regulators, charge pumps that goes in there as well. But if you were to compare SRAM versus DRAM, DRAM has much more analog components in it, I would say, as compared to SRAM.
Yes. Thank you, sir.
Yeah.
Thank you, Balaji sir,
thank you.
for sharing. You have shared very vast information about all the types of memory and all this. Thank you very much.
Sure, thank you very much. Thanks for having me here.